All right. So that's the agenda for today. So for the worksheet problems, we'll just have 5 of you that are willing to volunteer, come up and show your work, how you solved them. We'll check them together and make sure that everybody's on the same page. So let's see, where did I go? There we go. Right, and Lauren, can you see the worksheet on the screen, or do I have to switch the share? You can see it? Okay, good. I thought I had the settings right, but just wanted to verify. Okay, so can we get someone to come up and show us how you solved number 1? All right, Casey.
Is it writable?
You'll have to click on the draw up there, and then you can choose a.
Yeah.
Let me click on that real quick too. Get rid of that. There you go. All right, we all agree on this result? All right, so a couple things I'll just remind us of for just future reference. It's on the board, but we'll put it up here as well. Work on that board. Work equals force times the distance that force caused the object to move. And then in terms of units, we've got newtons and meters. And so he's put joules here for the final answer, just recalling that a joule technically is a Newton meter. So just making sure you're not forgetting that little detail, but everything looks good. Questions on number 1 at all? All right, so can we have a volunteer to come do number 2? All right, Nick. All right, looks good. Same equation. This time we've got 65 kN, which is kilonewtons. So 65,000 newtons times 75 meters. So we get 4,875,000 joules. Now, as we get through this unit on energy and work, we're going to often have really big numbers like this. And so I want to show you how, just briefly, how you'll often see this represented. So it's fine to have it there as 4,875,000, but often if you're checking like on an answer key or something like that, they'll convert that to 4,875 kilojoules. So just like we had kilonewtons at the beginning, they'll often represent it as kilojoules. Sometimes you'll even see mega, a capital M in front if it's billions. So, all right.
Would you prefer the answers in kilojoules?
No preference. Yeah, either way is fine. I just, sometimes if you're doing things on positive physics or whatever, you might see it different ways. And so I just wanted to point that out, that it may be required in certain online settings or different worksheets to recognize that they're the same meaning. But I have no preference in terms of what you write for that. All right, number 3, can someone show us that one? All right, thank you, Laura.
Thank you.
All right, so same kind of equation, or same equation, just solving for a different unit here, different variable. So we've got 30,000 joules, that's the work done, so we plug that in for W. We're looking for force, which is gonna be measured in newtons, we've got a distance of 9.5. So about 3,158, if we round it, newtons of force. Good, questions on number 3? All right, number 4, get someone else to volunteer for that one. All right. Thank you, Ashley. All right, very good. So using the same equation again, this time we have work and force, so we're solving for distance, and we should get about 9.875 meters. So questions on number 4? All right, last one, number 5. Two-step problem here. Can I figure this one out? You got it, Nick? What was your answer?
3,780 joules.
You got it.
Is it 3,000 or 8,000?
For the final answer?
Yeah.
I got 3,780.
Okay. No, I got 3780.
All right, so this is, at least for this first part of the semester, and then again, once we get towards the end and are reviewing for the final exam, you will still need to remember some of those kinematics things, like that you can find the distance by taking the velocity multiplied by the time if it's got a constant speed. So 18 seconds is the time multiplied by the 0.6 meters per second tells us it would travel 10.8 meters. And if that's the distance and the force applied was 350, we can multiply those to find out that would be 3,780 joules of work. All right, very good. Any questions about the worksheet? All right, make sure your name is on it, and then you can just stack them up here on the gray table here in the middle for me. Lauren, if you want to just bring it when you come back, or you can email it to me, whatever, either way is fine.
I want to be a good friend.
All right. Okay, so as I mentioned, the next thing we're gonna work on is taking some notes again on work and energy and power, focusing still on work and energy today. And then we'll look at pie charts and bar diagrams, and then we'll do that activity to wrap it up. So let's, if you're keeping your notes in a particular folder on certain paper, whatever, go ahead and get that prepared. And we'll start with some more information about work and energy. All right, so we're gonna start with a common example, someone lifting something up. So the work done by the person lifting this box would be the weight of the box, that's the force they would have to apply, right? So if the box weighs 50 newtons, they would have to apply 50 newtons of force to raise it. If the box weighs 100 newtons, they'd have to apply 100 newtons of force to raise it. So whatever the weight of that box is, that's the force we'd have to apply to lift it. And however high we raise it would just be the distance. So we've talked about how work is force times distance, but when it's vertical, the distance is the same as the height, right? So we can change the equation a little bit, and if we're lifting it vertically, the force we have to apply is equal to the weight. And we learned last semester that we can calculate weight by multiplying m times g. So we kind of have a new equation here. Where m is just the mass of the object, g is the acceleration due to gravity based on the Earth's gravitational field, and then h is just the distance it travels vertically, right? So it's a specific scenario. It's when we lift things vertically, but it's just kind of a modified version of F times D when we're lifting things vertically. Any questions about how we come up with that new relationship? Does that make sense? And now when we do work, if you recall from our definition, we transition the energy from one form of storage to another. And so in this case, when we do work on this box, we're actually raising a certain kind of energy. We're converting it into gravitational potential energy. That's going to be more of a focus for our lesson on Monday, but a little bit of foreshadowing today. So with the work that we do to lift something up stores that as energy in the object, and we call the way it stores it gravitational potential energy. So we'll just kind of foreshadow that a little today, give you a little preview today, and then we'll dig into that in more detail Monday. But I want you to recognize that it is both the work that we would do to lift it and the gravitational potential energy stored in the object once it's done being lifted. So, for instance, if I'm looking at this box, it has a certain amount of gravitational potential energy based on how high it is above the earth. And I can take it off the shelf and put it up on a different shelf, right? So I've done work because I've applied a force and moved it through a distance. And now it's got more gravitational potential energy because it's higher. So my work has increased its or changed its gravitational potential energy by putting it on a higher shelf. Right? So that's kind of a physical representation of what we're talking about. And like I said, we'll dig in more to the specifics of gravitational potential energy on Monday, but just want to start to get you thinking along those lines today. Any questions about that though? All right. If I take something off the top shelf and move it down, I'm actually decreasing its gravitational potential energy because it used to have a high height. So if I take this box of chalk up here, it's got a lot of gravitational potential energy up here on the top shelf, but if I move it down here to that level, now it doesn't have very much gravitational potential energy because it can't fall very far anymore. So if it fell off the top shelf and landed on my foot, it would hurt a lot more than if it falls off of where it's at right now, right? It would do more work on my foot if it fell off the top shelf and landed on my toe than if it just fell from where it's at. So it has more energy stored in it on the top shelf, less energy stored in it on the bottom shelf. So we can think about this both directions. When the force that I'm applying is opposite the direction of movement, we usually recognize the work as being negative. Now, work is not a vector like force or velocity or acceleration where we had to draw arrows and represent the direction. It's a scalar value, it's just a numerical value, but we still do use positives and negatives to indicate whether the force and the direction of movement were the same or opposite each other. So if the force you apply and the direction that it moves are the same, if I push up and it moves up, then that's going to be a positive value for work. If I am applying an upward force, but it's actually going down, so when I take this off the shelf, I'm applying an upward force, but if I lower it, it's actually lowering as I'm applying an upward force, right? So that would be negative work because it's moving opposite the way I'm supporting it. So if the force and the direction are the same, we consider that positive work. And if they're opposite, we consider that negative work. So have any of you ever parked your car? Well, probably not so much anymore these days because it's automatic, but maybe it's happened. You ever parked the car and got out and it wasn't in park? It starts to roll? Maybe?
Actually, yes.
A couple people, okay, so some people have been that way. It's more common back in the days when there wasn't automatic transmission, but it still can happen. So if you've ever felt that experience, so you jump out and you like start pushing to keep it from rolling, right? So it's trying to go one way and you're pushing it the other way. That would be negative work. You are doing work, but we would call it negative work because you're pushing in the opposite direction of its moving, right? If you've ever had to push a car to get it started, now that would be positive work because you're pushing it forward and it's moving forward. So if the push or the force and the direction are the same, we call it positive work. And if they're opposite, we call it negative work. All right. Any questions about that idea? Positive versus negative work?
Can you remind me what the MGH means again?
M is for mass,
Uh,
and G is the 9.8, the acceleration due to gravity, and H is just the height.
okay, that's what I thought.
Yeah. So it's actually 3 variables in one equation. All right. Anything else? All right, we'll keep moving. So we've talked a fair bit about work. We've talked about a definition for it. We've done a whole worksheet calculating work or using work to calculate force. We've defined it both as applying a force over a distance and how we change the energy storage in an object. But there's a relationship between work and energy that I want to emphasize today, and it's going to be even more important next week. And we call it the work energy theorem. The work energy theorem is this statement here right under the title that work done on an object is equal to its change in kinetic energy. Work done on an object is equal to its change in kinetic energy. All right, so the part there at the bottom is just reminding us that work has the units of joules, and we're going to learn today that kinetic energy also has the unit of joules. And I've previewed gravitational potential energy over here. It also has units of joules. So any kind of energy that we would measure or calculate is unit-wise going to be measured in joules. And any amount of work we do is going to be measured in joules as well. And that makes sense that they have to be the same because if we're saying that they're equal, that's really what the work energy theorem tells us. The work we do is equal to the change in energy. If they're equal, they have to have the same units. And so work is in joules, energy is in joules as well. We're going to prove that here in a few minutes with some unit manipulation over here. All right, so this next part, we said that one way to define work is how you change the storage modes of energy from one type to another, or you change the amount, like maybe giving it more gravitational energy than it used to have, gravitational potential. we're gonna define the main storage modes that you need to be familiar with one at a time. So the first one, and you've probably heard of the terminology before, kinetic energy, and you might see it abbreviated a couple different ways. The two most common ones are E with a subscript K. In other words, that'd be like energy that's kinetic. Or I tend to generally just write KE for kinetic energy. Both are fine. You can use either one, and you'll probably see both here and there on different worksheets and such. Does anybody have any knowledge about what kinetic energy means? Anything that you know about that already?
It's the energy that's already in motion.
Yeah, energy that's of an object that's moving. So kinetic energy is stored in the system based on the motion of an object that has mass, and every object's going to have mass, even if it's really small. So what do we measure mass in?
Kilograms.
Kilograms. And what do we measure the motion of something in?
Velocity.
Yeah, velocity in meters per second or something, right? So we're saying that kinetic energy is stored up in the motion of the object. Motion would be based on its velocity and the mass of the object, measured in kilograms. So keep that in mind as we come back to that here in a little bit. The next one is gravitational potential energy, and already started to foreshadow it here and mentioning it again here. We'll, like I said, dig into it more on Monday. You'll usually see this as an E with a sub G, meaning energy that's gravitational. Or sometimes they'll use a U with G, and I'm not really sure where the choice of the letter U came from historically. But often you'll see the letter U to represent any kind of potential energy. And so instead of E, they sometimes use U if it is potential energy. And so in this case, it's potential energy because of gravity. Now, I often just abbreviate it GPE, and so I also accept that. You can write it that way as well. Any of those are fine to me. But I want you to be familiar with what you might see in different charts and books and worksheets and stuff, so that you don't get confused when you see different representations. Unfortunately, one of the most confusing things about energy is books use all different kinds of abbreviations for it. There's not a real consistent one that you see all across the board. Like force is always just F, but energy, for whatever reason, there's lots of different representations of it in different books. Now, gravitational potential energy, because it's all about the gravity that Earth's force field generates, we can say that that's the energy stored due to the separation of two objects based on their mass. And so one of the objects we're usually talking about is the Earth. And so that's one of the two objects. And then the other object is whatever, like us in the Earth, or a bowling ball in the Earth, or a bird in the Earth, whatever. But usually one of those two objects is going to be the Earth based on the kind of problems we will solve. All right. The next form of energy is elastic potential energy. And you'll often see this as E with EL, so energy that is elastic. But because it is a kind of potential energy, you'll sometimes see it as U for potential energy with EL for elastic. And every once in a while, you'll also possibly see, so EL, you'll also sometimes see ES for spring, like because springs are elastic in nature, or U with the subscript S. So Unfortunately, this one has a lot of different possible abbreviations. So you might see the subscript EL, or you might see the subscript S for a spring. Now, it doesn't have to be a spring to be elastic. It could be a rubber band, or it could be a string, or anything that stretches or compresses. But since springs do stretch and compress, sometimes they will just replace it with S for spring. All right, so elastic potential energy is the energy stored due to the temporary deforming of an object, maybe stretching or compressing a spring, stretching a bungee cord, stretching a rubber ball or rubber band, compressing a rubber ball, I guess, stretching a rubber band. Anything that can stretch or compress would be able to store elastic energy. All right, the next mode, it's sometimes called dissipated energy. Sometimes it's called thermal energy, because usually when it's dissipated or lost, it's usually lost as heat. But it could be sound, it could be light, it could be other things. Usually it's heat, but because it can be other things, sometimes they'll use dissipated instead of thermal. And so again, a variety of different abbreviations for it. It might be E for energy or U for potential energy. And the subscript might be D for dissipated or TH for thermal. So lots of ways you could see it. All of them are acceptable, so you can pick and choose which ones stick better in your memory. And that is the energy stored due to the microscopic vibrations or motion of the molecules that make up the object we're talking about. So it might be vibrations that cause sound waves, or it might be vibrations that cause an increase in temperature. So if it's sound waves, it'd be more appropriate to call it dissipated, because sound waves don't create heat. But if it raises the temperature, then it makes more sense to call it thermal. So if it causes friction or something like that, then that would make sense to call it thermal. So that's the big chunk of notes today. That's the bulk. There's a few little details here and there, but that's most of the writing. Now you'll notice that the first three all have a little asterisk in front of them, and the last one doesn't. And I've noted them that way because kinetic energy has a particular equation, and gravitational potential energy has a certain equation, and elastic potential energy has a certain equation. But dissipated or thermal energy has no equation. You have to figure it out by basically process of elimination, or okay, it's this plus this plus this, so if I subtract all those things together, I can figure out what's left over. And the dissipated energy is always that left over a bit. So there's not a set equation like there is for the others. So kinetic energy, here's put some labels over here. We're gonna learn this a little bit more detail later, but kinetic energy has this formula. Gravitational potential energy has this formula. Elastic potential energy, which we saw E with EL, but sometimes I just abbreviate it EPE too, or as well. That's going to be 1/2. Stick with my same color scheme here so we can make it match later. 1/2 kx squared. And we're not going to worry about that one too much right now, but I just want you to recognize that all three of those first ones have a certain formula. Okay, dissipated doesn't. So you have to, by process of elimination, kind of figure out what it is. And that's where the bar charts and the pie charts come into play. Because if you know this percent is kinetic and this percent is gravitational, and that's all there is. Whatever's left over, that's dissipated. Okay, so they all three have a formula, but dissipated doesn't. And the top formula, obviously, or equation, that's work. So those are the four primary equations for this unit. We'll get one for power later as well, but it's a little bit different. All right, any questions about the energy storage types? All right, so before we go into the examples here and look at pie charts and bar charts, let's look at the units for these and see if we can figure out how this all works. So what is the unit for force?
Force, newtons.
Newtons. And what's the unit for distance?
Meters.
Meters, right? And we said that a Newton meter is the same as a joule. Right? So that was kind of our notes from yesterday. Well, what is mass measured in?
Kilograms.
Kilograms. What is g, acceleration due to gravity, measured in? 9.8
Meters per second
meters per second squared.
squared.
And height?
Feet.
Meters.
Meters.
Yeah, it could be feet if we were using imperial or English system. And what is kilogram times meters per second squared? That's a Newton. So really we have a Newton times a meter, right? Which is a joule. All right, how about this one? Mass is measured in kilograms. Velocity is measured in meters per second, but we have to square it. So that would be, I'm gonna write it kind of in a funny way, but that would be kilograms times meters, right? Meters squared is just meters times meters over second squared. But what's this?
Newton.
Newton. So we still end up with newtons times meters, still joules. We got all these different equations, but they all end up making the same thing, right? We're gonna save this one, we won't do this one today, but we'll save that one for later. Because we're gonna come back to, remember we did Hooke's Law with the spring lab that we did, where we stretch a spring? We're gonna come back to that one and revisit it with energy base, so we'll save that for that day, but it also will come out to joules. All right. Now let's talk a little bit about pie charts and bar graphs. So if we hold the ball above the ground and then drop it and just let it fall straight down, this down here at the bottom, we're gonna just think about the ball falling from being motionless to dropping and then right before it hits the ground. So not when it's hitting the ground or after it's stopped or anything, but just while it's in that falling process. So if we think about those four energy types, the kinetic, gravitational, elastic, and dissipated, what kind of energy does it have at the top when it's not moving, but it's held at some height? Let's just kind of go down through, we'll focus on these three, and then we also have dissipated energy. Does it have any gravitational potential energy if I'm holding it at some height?
Yes.
Yeah, because height is part of how we calculate it, right? So if it has some height, it's gonna have gravitational potential energy. If I'm holding it still, does it have any kinetic energy? Why not, Nico?
Because it has to be moving.
Yeah, there's no velocity, it's not moving, so can't have any kinetic energy. And then, am I stretching it or compressing it, or is there any kind of springiness to it at all? No, so the only thing it has at the top is gravitational potential energy. When I let go, it's going to start to fall, which means now some of that gravitational potential energy is turning into what? Kinetic, because as it falls, it's gonna have velocity now, right? And so as the height gets less, this gets smaller and smaller and smaller. That means this gets smaller and smaller and smaller, right? What's gonna happen to the velocity as it falls?
Fast.
Faster and faster and faster, which means this gets bigger and bigger and bigger. Okay, so as this gets smaller and smaller, this gets bigger and bigger. All right, so let me show you something here.
Mr. Webb?
Yeah.
May I please go to the bathroom?
Sure. So, Lauren, are you seeing the browser now in the, okay, good. All right, so we're gonna show a little simulation here, roller coaster simulation. All right. So we're gonna turn on a pie chart here, and we're gonna turn on a speed meter. I don't think we'll worry about the path there, but let's open up this bar chart. So we're gonna see a bar chart here and a pie chart here, and then just a scale here. And we're gonna drop this girl onto the track. And right now, as I'm holding her still, on the bar chart, what does it show in terms of energy? Just potential, yeah, gravitational potential. Is she moving? No, no kinetic energy. Is she compressing or stretching? No, so there's no elastic energy, it's just gravitational potential. But when I let her go, she rolls back and forth. And if you notice the pie chart above her head, it goes from being all potential to all kinetic at the bottom, and then back up to all potential. Just keeps alternating back and forth. And slow it down here so you can see the pie chart changing more. So all potential at the top, and all kinetic at the bottom, and then back up to all potential again. And so what do you notice about the total over here? Stays the same, doesn't change. So that's the conservation of energy, that we're not losing any energy to the environment. Whatever gravitational potential energy she has to begin with, it just changes to kinetic, and as she gets lower and lower and lower, the height gets smaller and smaller and smaller, so the gravitational potential gets less and less and less. And as she's falling, she goes faster and faster and faster, so the kinetic energy gets bigger and bigger and bigger. So as one goes down, the other goes up, and vice versa. Now, in real life, are any of you skaters? Do you go to skate parks or anything like that? I'm too uncoordinated to. I try it, but I just wipe out all the time. So if you do that, is this realistic? Would she just keeps going all the way up to the same height every time? No, she wouldn't in reality. If you notice over here, we've got gravity is tiny to lots, it's kind of in the middle, just normal gravity, and friction none. So we're saying there's no friction. Now that's where we lose the reality part. If we give some friction here, what you'll start to notice is she doesn't go up quite as high on the other side anymore. She goes a little bit less each time. And what do you notice over here on the bar graph? What's happening? Yeah, there's thermal energy. That friction's creating heat, and it's losing that thermal energy. What keeps happening to the thermal energy? Just keeps getting bigger and bigger and bigger. What happens to the total energy of the system? It's staying the same. So all that kinetic and potential energy she used to have that was just cycling back and forth is now dissipating. It's being lost to the environment because of the friction. And yet the total just stays the same. So as thermal gets bigger and bigger and bigger, the kinetic and potential keeps getting smaller and smaller and smaller. Eventually, what's going to happen? Yeah, she's eventually going to stop. So we go back to normal speed. Oops, I missed it. We go back to normal speed, so it's not quite so much time. We're going to see that potential and kinetic just keeps getting littler and littler and littler, and eventually she has no more motion, so she can gain no height on the ramp, and she just comes to rest, and all that motion, all that gravitational just has been lost to the environment as dissipated or thermal energy. all right? So that's the visual representation of what we're talking about here with energy transformation. The track is doing work on her skateboard to slow her down and slow her down and slow her down until all the energy she started with gets dissipated. All right, so back to our example here. The ball at the top has what kind of energy?
Gravitational potential.
Yeah, only gravitational potential because it's not moving yet and it's not being squished or stretched. How about in the middle?
Losing gravitational but picking up kinetic.
Yeah, it's losing gravitational but picking up kinetic. Does it have both?
Yes.
Yeah, because it does still have some height, but it's moving, so it's got both at that point. What about right at the instant when it's getting ready to hit the ground and it's basically reached the ground? What kind of energy does it have then?
Mostly kinetic. There might be just a little gravity, but it's gonna be
Yeah, if it's just at that point where it's starting to touch the ground, then its height now is 0 or really close. And so it basically has no gravitational anymore, and it's all kinetic. So here's how we would look at that on a pie chart. You would say it's got a bunch of gravitational energy, all of it, 100% of the pie. And then some point down, it's gonna have a mix. And as it falls, that pie chart's just gonna keep changing more and more kinetic and less gravitational. And then when it reaches the bottom, right as it starts to touch the ground, it's got a height of 0, so all of it's been converted to kinetic. Is that making sense in how we represent that? All right, so I'd like you to grab a whiteboard. If you want to use the smaller ones or the bigger ones, doesn't matter. Get a marker and something to erase with. We're going to have you practice some of these pie charts and see what you come up with. And Lauren, if you want to just do on a piece of paper, that's fine. All right, so I'm going to give you some scenarios, and I'd like you to try to represent what you think the pie chart would look like at the different spots. So this has 3 spots, so we do 3 different pies, okay? So you'll see the same thing for a variety of other scenarios and see if you get the idea here. All right, so here is our second scenario. A baseball is thrown up in the air and then falls back down. And they've already drawn the velocity vectors there beside to show that at point A, it's got a lot of velocity, and then here it's just got a little velocity, and then there it has no velocity, and here it's got some velocity downward, and here it's got a lot of velocity downward right before it hits the ground. Okay, so I would like you to draw the 5 pie charts for energy. What would it look like here, here, there? So draw 5 different pieces of pie, or not pieces of pie, but pie shapes with the division, and don't worry about it precise, like you don't have to put numbers to it exactly, but just want to see what you think the different energies would be at those 5 spots.
Do we include work?
Don't worry about work, just focus on these as your choices.
Okay.
Or you could add dissipated if you want.
Okay. What does the EPE mean again?
Elastic, so that would only matter if it's being squished or stretched.
Okay.
Give us a few more seconds to wrap it up. All right, so I've been playing a lot of games over the break because it was rainy and didn't go out and do much. So we played a lot of board games. So I got this little four-sided die. We're just gonna go by chance here. Who gets to show us your work? So this is row 1 and row 2 and row 3. And then Lauren, if we get a 4, you get to show us yours if we can. We'll see. You maybe hold it up to the camera and talk us through it or something. I can make your image on the screen better. And then the seats will be like 1, 2, 3, 4. So for you guys, just be you get the odd ones and you get the even ones. And if it's row 2, it's just 1, 2, 3, 4. And if it's row 3, it's 1, 2, 3. And if we get row 3, number 4, then I'll do it. All right, so that's my job. Okay, so we got first is row 4. So Lauren, right off the bat, you get to go. So I'll put, let me stop the share here. And we'll pin your picture so we can make it bigger. There we go. And you can just hold it up to the camera and kind of talk us through what you came up with.
It's kind of tiny, but it has like a small slice of EG, and then it has like the larger slice of EK.
Okay, for part A?
Yes.
Okay. Go ahead and hold up your drawing to the camera. I think we'll be able to see it. It's pretty big on the screen here.
Your fingers are blocking it.
Yeah, your fingers are on top of it there.
Oh, that was B, C, D, and E.
Oh, yeah, go ahead and show us all of it.
Oh, okay.
It's okay if you didn't finish it yet. Oh, it is kind of blurry.
Your fingers.
Yeah, it's okay. So what did you finish part B? What did you think about for part B?
It had a smaller slice of EK and then a larger slice of EG. And then I put EG for all of it for C. And then for D, I did like a small slice of EK and then a larger slice of EG. And then for E, I did a smaller slice of EG and then a larger slice of EK.
All right, very good. So we'll go back to the screen here. And let's go here. So it sounds like what you described is very similar to what we see here. We've got a lot of kinetic energy because it's got a lot of velocity and just a little bit of gravitational because it's not very high yet. And then up here we've got a lot of gravitational because it's pretty high and only a little bit of kinetic because it is moving but not very fast. And then at the top it's all gravitational because it's not moving anymore at the very peak, no velocity. And then on the way down, you might have different percentages, but here they're just showing, yeah, maybe half and half, but there's going to be some of each. And then down at the bottom, mostly kinetic, because it's a lot of movement with only a small bit of height. Okay, so hopefully you have something kind of similar to that pattern. Any questions about this first example? Making sense how it all fits together? All right, let's try another one. So here we have an object. It looks like a potato. I don't know. So we got an object resting on a coiled spring, and then the spring gets released, and that potato or whatever it is launches into the sky. And so we've got 3 times. So right here, the dot means that it's not moving. So right here, the potato is pressed the spring down and compressed the spring, but it's not moving. It's being held still. And then here the spring shot it into the air and it's part the way up and it's still moving. All right. And then here it's all the way at the top and it's at that point at the very peak where it stops for that instant. Okay. So draw your 3 pie charts. What would the pie charts look like in those 3 scenarios? Compressing the spring and not moving, and then up in the air moving, and then at the very peak and no velocity. And you can erase what you had before, you can draw it on another side or however you want to do it.
Can I have the restroom?
Just a few more seconds to wrap up your 3 pies. Should have brought pie today. Sounds good. All right, I'm curious to see what you come up with this, because we haven't really done one with spring energy yet, so I'm curious to see how you represented it. So let's see what you came up with. You got row 2. Let's see who's the lucky winner. Person 2. So Nick, what did you come up with?
Am I doing all
Yeah, show us all 3. If you want, maybe come step over here on the side so we can see a little bit easier. And hopefully, actually, maybe I'm not sure where it's going to be easiest for Lauren, but she hope she can hear you explaining it. Hopefully, so hopefully she'll be able to imagine what you're saying if she can't see it.
So potato 1, the spring is like there's all elastic potential energy. But this is just the spring is loaded and it has all this potential energy. Then it fires and then it releases, so there's none left, but it goes into the potato and this is the what kinetic energy?
Gravitational.
Gravitational. And then this is kinetic energy.
Mhm.
It's just half and half because and it's not really halfway up, but and then this is just at the top. It's not moving, but it has all the potential energy.
The gravitational potential. Yeah, good. Very nice. That's very similar to what they have here. They've got all elastic at the bottom, all gravitational at the top, and then some kind of split. You might have half and half, you might have 60-40, 70-30. Without measuring it, we don't know exactly the percent, but we know there should be some gravitational and some kinetic in that midpoint position. There's no more spring or elastic energy because it's not touching the spring anymore, it's just in the air. All right, any questions about that example? All right, now here's our last one. This is a challenge. So it says a super ball is dropped and bounces up and down. Draw a pie chart for each. You're going to have 5 pie charts, A, B, C, D, and E. And why does the ball not bounce as high each time? So if you think about what we saw in the energy skate park scenario with the person not going all the way up every time, what do you think's happening here? Where does that energy go? And if you notice down at the bottom, you can see here at the top, the ball just looks nice and round and nice and round and nice and round, but down here it looks like it's squishing a little bit. Okay, so see, how would you interpret A, B, C, D, and E for those 5 positions? And it's kind of hinted there in the red ink on the screen, but you probably want to think about that ED or ETH, that whether you want to call it dissipated or thermal. There's no equation for it, but that's that other kind of energy that we listed in our 4 types. Just a few more seconds to wrap it up. All right, let's see who our lucky winner is. Row 2 again. Person 4, Laura. Talk to us about what you came up with.
I don't know if I did this right at all, but for A, I did the GPE because it's at the vertex.
Mhm.
And then B, I did just all of the EPE, because like,
Elastic.
I didn't know if I should do kinetic as well, like I thought it'd still be moving, but it didn't, I guess.
Okay.
And then, yeah, it's just alternating between those two.
And then how about C, D, and E?
Oh, the same thing,
Oh, just alternating, I see.
yeah.
Gotcha. Okay. So I like the pattern there. I think that shows what's changing from those positions. Did anybody have anything added or different about that one? Gage, did you say you had something a little different?
Yeah, so I said every time for B and D, when it bounces, I said it adds like a really small amount of thermal energy.
Okay.
And then I also said that for C and E and then A, actually, it's just mainly gravity, and then as every time it bounces up, it doesn't get as high, so every time it slowly starts to decrease, it's just more kinetic energy being added on.
Okay. All right, good. So because it's not going quite up to the same height, it must be losing some energy somewhere. And we haven't looked at anything like this before either, so I was curious how some of you might try to think how you could represent that. So here is how they do on this curriculum. So they got all the gravitational there at the top, because it's just got a bunch of height, isn't moving there at the peak, at the vertex, like Laura said, and it's not squeezing anything, it's not moving, so it's just gravitational. And then down at the bottom, all that gravitational gets converted to elastic energy or spring energy, because it's springing the ball, it's like squishing the ball down. But since it doesn't bounce up all the way to the top, it must be losing some. And you could call it thermal energy, or you could call it dissipated energy. Because the ball would have a little friction on the ground, you'd probably hear it when it hits the ground. So it'd be losing some vibration energy there. And then when it reaches up to point C again, that thermal energy has already been lost. So that piece of the pie is already gone. And so we have to keep it there. Now the gravitational can't be the full pie anymore, because that thermal energy has been lost. So that piece of the pie it's like if you imagine looking at a pie and one piece is taken out, it's already got a missing piece, right? And once that missing piece is gone, you can't put it back. Okay, so that thermal is the missing piece, it's gone, and so now we can only have that much gravitational at part C. Does that make sense? And then if we go on to part D, it's going to squish the ball again, so there's going to be some elastic energy, but it's also going to make some sound vibrations and probably a little friction, and so it's going to lose more. It's going to have a little bit more thermal or dissipated energy, and so now there's going to be like two pieces of pie missing. And so when it bounces up to the height again, it can't quite go up as high as before, because now two pieces of pie are missing. So if we cut this into 8 pieces, there's only 6 pieces left of energy to reach to the peak. So if we thought about it as like dividing it into 8 pieces or something, or 6 pieces, however you want to think about dividing it, we keep losing some of the pie gets eaten away by that dissipated or thermal energy. Are any questions about how that works for this scenario? All right. So go ahead and put the whiteboards away. We're good with that. You can wipe them off and just put them back where they go. And you can pick up one of these papers while you're up moving around. And Lauren, I'll email it to you real quick here. And for those of you that are in the class, you can also grab one of these little spring chickens here. All right, so you can see if you can get your spring chicken to work okay. If you get one that doesn't work very well, you can swap them out. We got a bunch of them in there.
It's over there.
Whoa. There we go.
No, it's fine. This one doesn't work either. It's not sticking.
All right, so you should see that coming through, Lauren. Now it was computer's going real slow because it's recording here, but it finally went through. And one of the papers, Lauren, is just this picture here with these little toy spring birds. You've probably seen things like this before. And then the other side is a bar graph thing we're gonna work on Monday. So we'll just do this part today. As we wrap up today though, so you'll have to imagine it, Lauren, since you don't, unless you happen to have one of those little toys at your house, but what I want you to do is think through what you're seeing happen with these spring chickens and make your 7 pie charts on the handout there for what would the pie chart look like at each of these positions.
At B,
Mm-hmm.
is it at full extend?
Yeah.
Spring? Okay.
Mm-hmm. Yeah, it's not quite left the ground yet, but the chicken is actually like moving.
Yeah.
The base is still touching the ground, but the chicken part's moving. It's gonna be an estimation, I mean, there's no like perfectly right, you could have a slightly different opinion than someone else and still be, with your rationale, it could still be very good. Mhm. Say it again? Yeah. Mhm. You got a high jumping chicken? Now, if your parents ask you what you did in school today, you have something different to tell them. Yeah. Played with spring chickens. Talked about pie and spring chickens all day.
Can you pick up the
Orange.
Squish it the other way, like squish its beak. Is that better? What do you think, Dave? What do you think?
All right, so we're down to our last couple minutes. For Monday, I just want you to finish, if you haven't yet, finish those pie charts for the spring chicken example. Don't worry about the bar graphs on the back, that's gonna be Monday's lesson. But bring that back with you with those pie charts completed for Monday. And if you're done, you can just go ahead and put the chickens back in the box. And hope you have a good rest of your day. See you, Lauren.